Yo, what is up YouTube? In this video, let's try and learn how to solve linear homogeneous constant coefficient second order differential equations. So the first step to do this is define the characteristic equation. So assume that y is e to the rx basically, and with this we can write out the derivatives. Y prime is r e to the rx and y double prime is r squared e to the rx. And then in the most general case, we get like a r squared e to the rx and then b r e to the rx and c e to the rx, and that's all going to be equal to 0 on the right hand side since it's homogeneous. And then we factor out the e to the rx to get e to the rx. Ar squared plus br squared plus c equals 0, and we note that e to the rx is what y is, so basically y equals 0 is a solution every time, but this is a trivial solution. So let's go ahead and solve for what r is, and from there we'll get something meaningful to us. So the characteristic equation is this, and for us, we look at the coefficients. We see a is 1, b is -4, and c is 3. So r squared minus 4r plus 3 equals 0. We can factor this to r minus 1 and r minus 3, or r minus 3 and r minus 1, same stuff. R equals 0 and r equals r equals 1 and r equals 3 are the solutions. So we write y1 is c1 e to the x and y2 is c2 e to the 3x, and these are linearly independent functions, so both of them should be included in the general solution. In total, we have that y equals c1 e to the x plus c2 e to the 3x, and that's our final solution. Now let's take a look at something a little different where we have repeated roots from the characteristic equation. I don't know why I'm having trouble saying that word, but we quickly get this based on the coefficients, and we factor it to be r minus 3 and r minus 3 is equal to 0, which gets us the solution r equals 3. But it's a repeated term, so we have to take note of this special rule that we do. So we get y equals c1 e to the 3x probably is what should be there, plus c2 x e to the 3x. So the reason we throw in the x term there is to make these two solutions linearly independent, and this is a rule that's going to happen with these repeated root solutions. We're going to throw in the x on the second solution in the general solution. So c1 e to the 3x plus c2x e to the 3x is the solution to this one. Let's take a look at imaginary roots now. So here we have we have the characteristic equation r squared plus 4r plus 7 equals 0, and now we have to use the quadratic formula to find the roots because we can't factor this thing. So we have -4 plus or minus the square root of 16 minus 4 times 7 over 2a, which is just 2, which is equal to -2 plus or minus the square root of -12 over the square root of 4. And the square root of 4 is just 2, and we wrote it that way so we could put it under the root. So we have -2 plus or minus the square root of 12 over 4i, and we pulled out that I, which is the negative square root of 1, and this is our two solutions. So we could write it like this: y equals c1 e to the -2 plus root 3i t plus c2 e to the -2 minus root 3i t. But we don't want to write it this way, and there's a couple reasons for that. We're missing some kind of sinusoidal behavior if we write it in this way. It's hard to see, and we're also missing it's like an imaginary solution, and we don't like those. So we're going to use this general solution form: c1 e to the lambda t cosine mu t plus c2 e to the lambda t sine mu t, where lambda is the real part of the root, so in our case it's -2, and mu is the imaginary part, or not necessarily the imaginary part, just this thing connected to the y, and that's going to be root 3 for us. So our final solution is c1 e to the -2t cosine root 3t plus c2 e to the -2t sine of root 3t. And a special note here is the general form is lambda plus or minus mu I. So we're going to look at this. When we have a solution like this where we have a real and an imaginary part, mu is like the magnitude in front of y pretty much, and lambda is like the real part. So yeah, that's that.